Okay. So that multiplication table. I'm going to do an example like it, because I don't want to do that problem for you. So what if I had base 3? Okay, so I got 0, 1, 2, 0, 1, 2. Times. Zero times anything is, yeah, so 0, 0, 0, 0, 0. Oh yeah, I forgot one. Okay. You guys with me? That was a gimme. That was a gimme. It wasn't add, so a lot of guys misinterpreted it as add. It's times. So that's a gimme. And then the ones are a gimme. Yes? Oh, I'm sorry. It is a give me. It is a free spot. It is a. Does that make sense? Yeah. Yeah. The ones are a gimme. Why? 1 times anything is. 1 times anything is itself. So 1 times 1 is 1. 2 times 1 is 2. So whenever you have the ones, they just repeat. 2 times 2 wants to be 4. We're in base 3, yeah? It's 11. 2 times 2 is 4. 3 would be 10, correct?
Right.
So even better, watch. How would you show a student to do this? One trick you could do is count by 2s, yes? 0 plus 1 is 2. 2 plus 1 is? 2 plus 1 is? 2 plus 1 is? 10 plus 1 is? 11. So we counted on by 2, didn't we? So for you guys, the third row is going to have that happen, if I remember correctly. You have to count by 3s. So you're going to have 0 plus 1 plus 1 plus 1 is 3. What's 3 plus 1? And base 4. 10, and then you have to do 11, 12 to go the full 3. You guys see what I'm saying? You have to count by 3. Now, as weird as that is exactly as weird as learning base 10 is for somebody who's never seen it before. And to be really honest, it's actually a little more weird. So it's really good to have a place to come from of empathy. You have to really understand from your student's perspective how trippy it is, right? You guys follow? So you need to understand why they're having trouble with certain things. Bless you. There are unfortunately teachers that teach that just don't understand. Why can't you guys remember 2 times 6 is 12? And you're like, because this is all weird. What do you want from me? Yeah, sorry.
You said count by 3, right?
Yes.
Okay.
So in base 4, if you start at 0 plus 1, 2, 3 is 3. 3 plus 1 is 10. Plus 1 is 11, plus 1 is 12.
Okay.
So that row should be 0, 3, 12. Yes, and then you can count by 3 again. What's 12 plus 1? 13 plus 1. 20, good. Not 14, what happens when you hit the base? The next number rolls over. Plus 1 again, 21, and that's why I have a 21 in that next question, yes? Okay, and that's the one you're talking about.
Yes.
Does that help?
Well, no, I understood that. I just didn't understand it.
So if you use this, do this. 21 divided by 3 must be. What does it take to make 21? 3 times. 3 times 3, right? Yes. Oh, I see. You got this. That's 1. Yeah. 3 times 1 is 3. 1. 7? What's your 7 say? Is that the A times C?
I thought I understood it, but then I was like,
I'm gonna make this relate. Guys, is everybody's number 7 the A times C problem? The one where I gave you a division.
Oh, yes.
Yes? Okay.
Wait, what happened? What were you asking?
Is everybody's number 7 the A times C question? Okay. So one person made a concrete problem that related to what I gave them, and then they could actually just see what happened. Right? And you didn't have to do that. In fact, I didn't even think about that. But I was like, holy shit, that's awesome. Right? So, help me out, guys. 8 goes into 37. How many times? 4. Remainder 5, yes? So what is 4 times 8? It's going to be 5 less than this, yes? 4 times 8 will be 37 minus 5, because the remainder always tells us how much bigger this number was in order for this to go in evenly. Do you see how that relates to your A times C problem? Directly. Okay. So now if I did this, and I said what, oops, sorry, B. If I said what's A times B, it would be 37 minus 5. Yes?
Yes.
Okay. Okay. So it's just an understanding what the remainder, how it relates to the rest of the problem. So if I take some of the concrete numbers out of the way, I can really tell, do we really understand what the remainder tells us in general? Not in a specific problem, but what does it tell us in general? It always tells us how much more the inside is in order for the outside number to go in even. Yes?
Can you explain 3B?
That's the one I can't. No, I'm joking. Let me see. 3B. Is that one about the student doing weird things with exponents?
3 raised to the 4 times.
All right, guys. So, did you really not bring any paper for yourself, Jeff? Oh, here we go. I got some paper. Let me see. Help me out, guys. This is going to be stupid here to begin with. How many, no, let's not use 4. Let's use, yeah. How many 15s can I make with a 5 and a 3? I can make 1 15. If I have 2 5s and 2 3s, how many 15s can I make? I can make 2 15s. Is everybody with me? Doesn't that just make sense? For every 5 and every 3, I can make a 15. So if I have 2 5s and 2 3s, I can make 2 15s. Now, real quick, you wouldn't necessarily think to do that. I love most of you guys did talk about order operations. What I needed from you is, what did the student do? What did they misassume, or what did they apply correctly? And you're going to have students who are going to do some shit that you don't even know what the hell they did. And it's going to be good. It's going to be correct. It's going to be correct. And the last thing I want you to do is to shut that student down. You understand what I'm saying? Because you've lost an opportunity to say, wow, I didn't even think to do this. You've lost that chance. You've not given that student the props for coming up with something creative. Do you guys see what I'm saying? And you've shut them down a little bit for their future math stuff. Because on their end, they're going to be like, I thought I really understood that. I guess I don't. All right, I'm just going to do it the way that they don't. You've shut that down. You see what I'm saying? Now, again, you can't possibly be everything for every student. But you can generally try to not do that. You have got to connect with your students' thought process. You have to know how far or how close they were. If they got the wrong answer, you still need to know how close or how far were they. from getting that right answer. Does that make sense? Okay. You might have gone through this yourself. You have had teachers, I have had teachers who sucked. And I just was lucky to get through them and still have an interest in math. Or still had an appreciation of my own creativity with the math. Yes? Okay. So if I have this, can I still make some 15s? Can I still make some 15s? Can I make 3 15s? Why can't I make 3 15s? I don't have enough 3s. But how many 15s can I make? But what's going to be extra? Yeah, there you go. Isn't that what that Part B student did? Look back at Part B. That's exactly what that student did. Which, listen, it's neat. It might not be what the question said to do. You follow? The problem might have said, simplify this. And they were supposed to raise stuff to a power and then multiply. I don't give a shit. If they do something, you have got to take the time to say, what did they do? That's interesting. Okay, you got it wrong because the instructions wanted you to do this, but what you did was kind of nifty. It was a really cool idea. Do you guys see what I'm saying? Maybe? No? See? Screw you, Jeff. I'm not going to do that. Alright. Oh, nobody's they better do what I say or I'll screw them. Does that make sense for Part B? You see how that's exactly, somebody actually kind of like didn't read it right, but it was funny because they talked about where'd that 2 come from? I'm like, that was the extra 2, that's the extra 2, right? Yes?
Why would you multiply 5 instead of add 5?
There's no addition. Is there any addition in this problem?
No.
Okay, so watch what I did. I literally did this, well, let's see, okay, you agree that there's 5 squared times 5? Is that cool? 5 cubed is 5 squared times 5. You with me? Okay. And then can't I move these, can't I use commutativity? And what did we just say this is? 15 squared times 5. So one level, of course it's times, because that's the only operation. If I'm just putting together parts of a multiplication problem, then the parts I didn't have to still be multiplied. It's all multiplication. Yeah. Like it. See, the more people that do the homework, the more chance there is I'm going to get a question about a problem that isn't immediately obvious. The person who asked that question will be a hero for roughly 12 other people. Those 12 other people were too shy or didn't feel like asking. You with me? But if there's less people that are actually doing the homework, there's less chance for it to happen. I don't see where there's a problem. Okay. Yes, they get it, Jeff. Do the homework. All right. Yes.
I have a question. For 12, you put 2 specific.
Yes. All right. That's the other one I thought I'd get some questions about. 12 is the one about A, B doing stuff.
Yeah.
What was it like? Was it 6 divides 2?
2 is divisible by A.
Does 2 divides A? Yes.
Divides A.
6 divides B. Yes.
Plus divides 1.
Yeah.
Parentheses.
Yeah. So a lot of you guys were talking about relatively prime stuff, which was kind of good, but this is not the place to do it. If 2 divide, now real quick, stay with me. Does 2 go into 6? I'm sorry, wait. You can do it, Jeff. Can you? Yes. Does 2 go into 12?
Yes.
Does 4 go into 12?
Yes.
Does that mean 8 has to go into 12? Because 2 and 4 are relatively prime. So, doesn't necessarily, it's not new information. If I know 4 goes in, I automatically know it goes 2. But that's not this problem. Are both 2 and 6 going into the same number? 2 goes into what number? 2 divides what number? When I say number, you don't know what the number is. What does 2 divide? A. 2 divides the number A. 6 divides the number B. They divide separate things, yes? You guys with me? If you gave yourself numbers, that is automatically too specific. Because I said must 12 divide AB. So it has to be for every possible A and B. So if you want to go that route, you have to try every possible A and B. I don't think you should do that because you would still be doing it. You guys with me? But how many things could A and B be? Infinite number. Okay. Are you guys with me? Okay. What does it mean for 2 to divide A? What does that mean? 2 goes in A. What's another way to say it? Why does 2 divide 6? Because 2 times, why does 2 divide 6? Because 2 times 3 is 6. So if 2 divides A, that means that 2 times something is A, yes? Alright, 6 divides B, what does that mean? Something, and what should I put? Should I put M? No, because we already put M. It doesn't have to be the same M, does it? 6 times something is B. Are you guys, is that cool? Is that alright? That's what divides, that's one way to look at it. If one number goes into another one, that means there exists a number that the first number times that is that number, is that last number. 2 divides A means 2 times something is A. So what did I say? A equals just right there. What is A equals to? 2 times M. And what's B? And we're investigating what? So what's A times B? What's A? 2M. And what's B? What's that? What's 2M times 6M? That's what AB is, correct? So does 12 divide that? I don't give a shit what M and N are. 12 divides that because I see a freaking 12. I don't know why I just did the whole problem for you. I like them. I love them problems, so I couldn't. I had to. When I say one number divides another, that means that the first number times something is that last number. I can automatically write that. That's a known thing. There is nothing wrong with giving yourself a concrete example just to feel the problem out. But you can't use it to prove anything. It's too specific. Really quick, so why is what I did okay then? Just because I'm a math boy? Just because I'm teaching the class? Yeah, you get it. I'm always right. No. So, how many A's did we say there could be? Infinite. 2, 4, 6, 8, 10, 20, 80, 35, 30, 50. Yeah, any even number, correct? As big as you can imagine, and then you square it, and then it's even bigger than you can imagine. But look what I just did. Look how many numbers did I just write down? A equals an infinite number of things, because how many things could N be? So I just wrote down every number that A could be. That's the power of variables. A is twice M. Doesn't that say A is an even number? Yes? A is twice M. A is an even number. B is 6N. B is some multiple of 6. Then I just represent every possible number that could be there. Okay, I'll stop. I'm sorry. So, if you're paying attention, that correction is easy. Anything else from the test before we? Anybody come in after I gave up all the tests? Anybody still need their test back? Oh. I said your name like that because I have a student named Elvia.
Oh.
So I was like, okay. All right, guys. Go ahead and put those away. There's no other questions. You got time to work on the corrections? Do you guys know you can go get help with the corrections from a tutor in the math science? Do you guys know you can get help with the corrections from me? Holy shit. Okay.
I know. Put it backwards.
Shoot. Oof. Can somebody help me out? Can somebody do, I didn't, I'm a math guy and I didn't bring a calculator with me. Can you do 48? Somebody, anybody. 48 times 81 times 7 times 121. Yes. What'd you get? 293. Sorry.
136.
Good Lord.
136.
That's it? Trillion, billion, million, zillion. Okay. Is that it?
According to calculator.
Gotcha. Okay. We'll trust the calculator.
Right.
So, can you guys, a little motivation for our part of today. Can you guys imagine how long the list would be if you try to write all the factors for this? Huh? No. Can't be an infinite number of factors. Right? And real quick, what's it mean to write the factors? What are the factors of 12? 1, 2, 3, 4, 6, 12. You guys with me? So let's start. Let's look at 12 then. All right. So let's put this aside. If all I want to know is how many factors, if that's all I wanted to know, it'd be great if there was a shortcut so I wouldn't actually have to list all the factors. Do you guys understand? Because how would you start to list all the factors? Okay, it's even, so 2 goes in. So 1, 2. Does 3 go in? Let me add them all up. Can you see how long that would take? Okay, so if my only question is how many factors does this thing have? Is there a shortcut to get there? Do I actually have to write the whole damn list of factors out? The answer is no. So if I start with 12, can you guys prime factor 12 for me? 3 times 4. Good. So 12 is 2 squared times 3. Okay. Do you all agree with me, for example, that 3 is a factor of 12? Okay, now listen. I'm going to do something a little tricky. A lot of what we do in here is we talk about stuff you did when you were little, you've forgotten, or I talk about stuff you've never heard of before. Yes? And I understand those two are both freaky. Okay. But let this in. 3 is a factor, correct? Okay. How many 2's does 3 have in it? We'll try this again. Do y'all agree that 8 has 3 2's in it? 2 times 2 times 2? Does 7 have any 2's in it? Nope. You with me? Because there's no factors of 2 that go into 7. Are you with me? So, how many factors of 2 does 3 have? It's a weird question. None, yeah? I know it's a weird question, but 3 don't have no 2's, Jeff. It's a freaking 3. You with me? 4 has 2 2's, 3 has none. Okay. So watch this. This is gonna be the long way, and then we're gonna make a shortcut. I can make all the factors of 12. I can make them. If I take no 2's times no 3's, I get 1. Is that cool? What's 2 to the 0? What's 3 to the 0? 1 times 1 is 1. Do you all agree 1 is a factor of 12? Okay. All the factors of 12, does everyone agree that all the factors of 12 have to have 2's and 3's, if anything? Yes? So one thing I could do is I could take no 2's and no 3's, and that makes 1. Or I could take no 2's and 1 3. What does that make? 3. Okay. Or I could take 1 2 and no 3's. What does that make? 2. Or I could take 1 2 and Jeff, you could do it. 1, 3, what does that make? Or I could take 1, 2, and, I'm sorry. All right, I want you with me. No 2s, no 3s. No 2s, 1, 3. And the most 3s I can have is 1. Is that cool? And then I could do 1, 2, no 3s, 1, 2, 1, 3. And now I could do 2 2s, no 3s, 2 2s, 1, 3. What's this? 4. And what's this? 12. So there's all the factors of 12. 1, 2, 3, 4, 6, 12. Yes? Okay. 2 things just happened. One thing is you're out there saying, my God, can this guy just speak normal? Why the shit does he always have to sound so weird? I'm sorry. Does everyone see what just happened? This is kind of cool. This is something you guys don't get to see directly anymore. I could put together the factors of something in different ways. That's exactly what this is all about. If you understood this, you would have had an easier time with like factoring trinomials in algebra, because it's all about playing with the factors. Yes? Times, sorry. My little dot got extended. Yeah, multiplying all these together. Yeah. So, let me ask you, how many options are there for the number of 2's I could use? How many options were there for the number of 2's I could use?
2.
You sure?
3.
I could use no 2's, 1, 2, or 2 2's. So how many options were there? 3. And how many options were there for the number of 3's I could use? 2. So read it with me. Okay, I really want this to make sense. So it makes sense. How many factors did we end up with? How many factors did we end up with? 6, right? That's 2 times 3, yes? So if I have 2 options, so for example, has anyone ever bought let me see. I was going to say a car. Has anyone ever dreamt about buying a car? Have you ever thought about colors, like the color on the outside, the color on the inside? Are you with me? Okay. So say I have 2 options for the outside color of this car, and 3 options for the inside. With me? Okay. So how many total different color combinations could I make? So for every color on the outside, there's 3 in the inside. Right? So if I pick a color here, there's 3 options there. If I pick the other color, there's 3 options here. That's 6, 2 times 3. Yes? So when I have so many ways to do this first thing and so many ways to do the second thing, I can take all the ways and multiply them, and that gives me all the ways. Are you with me? That's how you end up with like 7 million possible combinations of pizza toppings if you have 11 toppings to choose from. You're just going to multiply all the shit together and it gets crazy big, which is really kind of amazing. Okay. Let me stop. Dear God, Jeff, tell me this is shortcut. Okay. Do you notice how, even though this says 2 squared, there's 3 options because I'm counting the 0? Do you see that? Wouldn't that happen every damn time? So if all they want to know is how many factors are there, you break the number down, you take each power, and you add 1 to it. And then you multiply them. Jeff. 3 times 2 is 6. So there's going to be 6 factors here. Yes? So what if I told you, so let's try an example. You're never going to have to do this. Do you understand what I just said? You're never going to have to do this. This was to try to make this make sense. Since I always count 0 as an option, there's one more option than that number. And then I multiply like I just explained. Why do you multiply? So what if I told you that this factors to be, all right, pass Jeff, there you are. That factors to be this, yes? You with me? Okay, so what if I just wanted to know how many factors it has? How long its list would be? That's all I wanted to know. What would I do with each power? Same thing we did down here for the same reason. Just add 1 to each power. What's this power? and then multiply, right? There's 5 options for the number of 2's I can use. Does that make sense by itself? How many 2's could I use to build? I could use no 2's, 1 2, 2 2's, 3 2's, 4 2's. That's 5 options, correct? 5 options for the first, and for every one of those, there's 6 options for the number of 3's. For every one of those, there's 2 options for the number of 7's. You guys see that? Because I can either use no 7's or 1 7. So for example, what is an obvious factor of this number? Do it again. 3? How do you know that? Without looking at this, how do you know if a 3 goes into this? Nope, the 6 at the end doesn't mean anything.
Yeah,
How do you check to see if 3 goes into a number?
yeah, all the digits.
5, 14, 17, 18, 21, 27. 3 goes into 27, so 3 goes into this. You with me? So do you all agree? Oh, I'm sorry. If you add up all the digits and it's a multiple of 3, 3 goes into it. What's the only other number that has that same rule for itself? No. 9. Right? If you add up all the digits and it's a multiple of 9, 9 goes into it. I added up all the digits, I got 27. Is that divisible by 9? Is that a surprise considering we already know it's got freaking 9 in it, correct? Does it have 2 3's in it? So it's got 9 in it, don't it? What's the rule for 6? 6 has got to match the rule for 2, and what's the rule for 2? Is that even? Yes. And it's got to meet the rule for 3. Does it meet the rule for 3? Yes, so 6 goes into it. And of course 6 goes into it. Can't I make a 6? If I take 1, 2, and 1, 3, isn't that a 6? So 6 is a factor of that number. Right, so earlier you told me 3 goes in. How many 7's did I use to make that? None of them. How many 11's did I use? No 11's. How many 2's? No. How many 3's? I used 1 3. So does 21 go into that number? Why? What 2 things go into that number? 3 and 7. So does 21 go into the number? I can take 1 3 and 1 7. 21 goes in. Yes? Do you guys start to see? Does 33 go into that number? Why? I can take 1 3 and 1 11. Yes? You see? Does 22 go into that number? I can take 1 2 and 1 11. Cool. Okay. Does 49 go into that number? 49. Why not? I can only use how many 7's? 1. So can 49 go in? No. If you try to divide by 49, you'll get a decimal remainder. Yeah. Okay, let me stop for a minute. When we make a list of factors, very often we're working with small numbers, so we don't even think about it this way. But when we get these big ass numbers, I can start to make a list of factors by recombining its prime factors. Yes? Maybe? No? Sure, let's try one that's a little bit smaller. Let's do, you can do it, Jeff. Let's do 42, sure. Can you prime factor this for me? Yeah, 7 times 6. 2 times 3, so I got 2 times 3 times 7. What's every power? Every power on the numbers. 1, 1, 1. So how do I figure out how many factors 42 has? That's all I want to know. I don't want to know what any factors are. I just want to know how many there are. No, no, no. What's the process? What's the process? Add 1 to every power. And then do what with those? Multiply. Why do we do that? Because of the first thing I showed you. Yes? How many 2's could you use? Let me try it this way. Can you guys take 2, 3, and 7 and tell me a number that goes into 42? No, so one answer could be 7, right? How many 2's did you use to make 7? None. How many 3's? None. How many 7's? 1. Can somebody else give me a bigger number that goes into 42? 2. How'd you make 21? You used 1, 3, and 1, 7. How many 2's did you use? None. Yes? If I know the prime factors, then I can create the smaller factors that go in there. So how many options do I have for the number of 2's I can use? None or 1? So there's 2 options. So how many options for the number of 3's I can use? I can use none of them or 1 of them. Yes? Do you guys see? I always add 1 to the power, because then I'm adding the option that I could just not use any of them. Yes? You guys got with me? So if I have 2 people, and I could choose any number of these 2 people to go with me somewhere, how many people could I choose? 2 or 1 or none. I could say, you come with me. I could say both of you, and you, and I could say, nah, you just gotta stay here. Right? None is an option, and that's why it's always 1 more than what I see. There's 1, 2, but I could use none. So of course, I'm going to add 1 to the number of 2's. Okay. So then I get 2 times 2 times 2 is 8. I'm just trying to make the list of factors. Not a prime factorization, but just a list. So I got 1, 2, 3. Does 4 go to 42? 6, 7. Now watch. Stop. This is kind of cool. You guys, we've done this before, yeah? You guys have done this before, just make a list. But do you guys remember how difficult the first part is? Do you guys see what I mean by the fact that we made the turnaround? We have hit the turnaround. What does 7 go with to make 42? 6. So once you get it high enough, then you just start pairing them off. 6 goes with 7. 3 times what is 42? 14, yeah. Real quick trick. You all agree 6 times 7 is 42, yes? If I divide 2 by 2, Jeff, you can do it. If I divide 6 by 2, I get 3, correct? If I give that 2 to 7, I get 14. So 3 times 14 is 42. If 6 times 7 is 42, then 3 times 14 is 42. Yes? Okay. And then 2 times what? 21. And then 1 times 42. How many numbers did we end up with? Holy shit. 8. Yes? Okay. If you make the list, you should end up with this many. This is a good thing to know how to do when you're a little human who's supposed to make this list. I'm like, I'd love to know ahead of time so I know if I missed one. Well, if I know ahead of time I'm supposed to have 8, I'm like, I have 7. Oh shit, what did I miss? Right? If you have no idea, you're like, it sounds good to me. All right, let me stop. All right, let's try another one. Has everybody got what they need from here? This was me just explaining how to get, if I know 6 times 7 is 42, divided by 2 times 2, 3 times 14 must be 42. Okay, so here, you guys do the same process. Don't make the list of factors, just how many factors will this have? What, Jeff? I don't know, man. Let's do, yeah. No, let's do, yeah. Sure, we'll just do that. How many factors would this have? If I had to make a list of the factors. So what's the first step? Just make sure everybody's on the right track. What do you do with 90? Make a prime factor, right? So do that. Even if you're not sure what to do after that, just make the prime factor. You guys get that? 2 times 3 squared times 5. Right? Right, now how do I tell how long those factors will be? What are the powers? What are the powers? What's the power here? 1. There's 1, so what are the powers? 1, 2, 1, yes? So then, to figure out how many factors, Jeff, you can do it, buddy. I'm just going to cut to the chase. 1 plus 1 is 2, 2 plus 1 is 3, 1 plus 1 is 2. If I just multiply those together, I can see how many factors it's going to end up having. Yes? Okay. Do you guys know how they calculate the odds for winning the lottery? You can do how many options are there for every number you pick, and then you multiply that together. Because for every option for the first one, there's so many options for the second. That's the definition of multiplication. For every crate, if I put 2 things in each, then I got that many times 2. So how many fractions do we get? Yeah, 12. So if I do make the list of factors, there will be 12 factors. If I do this, there will be 12 factors. Yes?
Where'd you get the 2 and boxes?
Oh, where did I get any of these?
Well,
Well-
actually,
Good.
I was assuming that the first 2 came from the.
Oh,
first.
no, hell. No. What are the powers? 1, 2, 1.
Oh, so you, okay.
1 plus 1, 2 plus 1, 1 plus 1. So watch. If I take that away, all right, I'm not sure how else to say this. If I take that away, what number is this? What is this? What's 3 squared times 5? Yeah, 9 times 5 is 45. 45 goes into 90, yes? That many times, of course. So if I use no 2's, 2 3's, and 1 5, I do make a number that goes into 90. Of course I do. So I could use no 2's or 1 2, no 3's, 1 3, or 2 3's, no 5's or 1 5. And that's where these come in. 2 options for the number of 2's, 3 options for the number of 3's, 2 options for the number of 5's. Okay. Here, let's try to make that. I'll show you one more neat little trick. Let me look back up here. Can you guys identify what I mean by the turnaround point? Can you guys identify the turnaround point? Where did I stop trying to come up with numbers and I just started pairing them with things before? 6, right? Right after 6, I started doing 7 and 6, 14 and 3. Yes, that's where things become a little easier. Yes? What's the square root of 42 roughly? Can you do the square root of 42? No. You agree with me? Yes? What number is below 42 that you can do the square root of? 36. What's the square root of 36? So where will the turnaround point always happen? It will always happen around the square root of the number. The square root of 42 is kind of 6. It's a little bigger than 6. So that's where the turnaround point is going to happen. What's the, if we look at 90, what's the square root of 90 roughly? What's the number below 90 that you can do the square root of? 81. What's the square root of 81? So when I start to make my list of factors, when I get to 9, that should be roughly where the turnaround point happens. So what are some factors of 90? 1 goes in, does 2 go in? Hell yeah. What about 3?
Yes.
Damn straight. What about 4? No. What about 5? Hell yeah. What about 6?
Yes.
Why does 6 have to go in? Because 2 and 3 go in. I like it. What about 7? No. What about 8? No. What about 9? Yes. And we said the square root of 90 was roughly 9, right? And do you see how this is the turnaround point? Because 9 times what is 90? So now I can stop thinking as hard, because now I can just start pairing them, yes? The first part of a list of factors is always the harder part. Because you actually have to think, okay, does this go in? Does this go in? Now you can just start pairing them. 9 times 10, 6 times blah, blah, blah. Blah, 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 blah. Blah, 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 blah. Sorry, stop. So 6 times what is 90? Let me see if I can get anybody on board. You all agree 9 times 10 is 90? Isn't 9 3 times 3? Isn't 10 2 times 5? I'm sorry. You guys with me? So isn't this 6 times, you can do it. This is 6 times 15. Do you see that? Do you see it? You can play with the stupid little building blocks to build other shit. That is the idea. Right? And listen, has anyone ever seen what I just did? Do you think, right? All right. If what I just did doesn't make sense, let me know. We all agree 9 times 10 is 9. 9 is 3 times 3, 10 is 2 times 5. I can reorganize that shit to get another set of factors. 3 times 3 times 2 times 5. So 3 times 2 is 6. 3 times 5 is 15. So 6 times 15 is also 9. Do you guys see that? Screw you, Jeff. So real quick, I really want this to make sense. And a few of you guys are looking at me like, please just tell us we can go home early. You all agree that this is 90. 9 times 10. Commutativity works for multiplication, correct? So I can make this 3 times 2 times 5 times 3, yes? This is, so 6 times 15 is 90. 5 times what is 90? Well, I can do the same trick. What's 15? 5 times 3. Bring this over here. 18 times 5 is 90. Do you guys see that? Is that an obvious pair of numbers that multiply by 90? No. If I said, give me 2 numbers that multiply by 90, if anybody said 18 times 5, I would have been like, oh, cool. Wow, cool shit. That's not the first thing that comes to my mind when I think freaking factor 90. Do you guys see how I got it? It's just re-putting together the factors. So this will be 5 times 18. 3 is easy. 3 times 30. 2 times 45. And then 1 times 9. Okay. How many numbers did we just write? On my little number candelabra there. Candelabra. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Isn't that exactly how many we predicted? Isn't it nice to know ahead of time there's supposed to be 12? So if I forget one, it's damn easy to forget one. Right? Okay, maybe. Okay. All right. Sorry, did I take it way too soon? So bear with me. Okay. So if I had this number, could you tell me, whatever that number is, how many factors it would have? How would you do it? What are the powers? So I would do what times what times what?
5 plus 1, 6 times 3 times 2.
Because again, now listen, I could have just said that, right? I could have just said, yeah, just add 1 and multiply. I have to show you the reason why. And really, the whole reason why is we also count not using any 5s. So I could use up to 5 5s, you agree? If I multiply it 6 5s, I'm not going to get a factor of that number because it's got more 5s than it should. You guys agree? Maybe? Like, if I try to make 8 and I use 4 2s, I'm going to make more than 8. I've got one extra 2, correct? So I can't use 6 5s. But I can use 5 5s. Right? I can use 5 5s, 4 5s, 3 5s, 2 5s, 1 5, or no 5s. And that's why we add 1. We count the option that I could just not use any of them. Right? Just like we had 2 people, but there were 3 things I could choose. One of them, 2 of them, or none of them. There's one more option for me, yes? Okay. And then, what is this? Sorry. Okay, so if I try to make that list like we did up here, I probably have to turn my paper like this. I would have 36 of those bad boys running around. Okay. Yes?
Really fast. Just so I get it right, you said the turnaround starts at the nearest.
Square root of the number, yes. Cool. Do you guys understand that and think that's kind of nifty to know? Whatever I'm trying to make a list of factors of, if I take a square root, I see about where the turnaround point. That's a really good thing to know. Okay. All right. By the way, all right. This is an example. All right, listen. Even if you don't fully understand everything I talked about. Yes, sorry, go ahead.
Random question.
Yeah.
What if the number is a square root?
Okay, beautiful. That's going to be my next example, but let me, hold on. Because every time we made a list of factors, have you noticed there's been an even number of factors? Does anyone notice that?
Yes.
Yes, okay. So, what was I about to say? That's all right, John. What if I had a square number, so like 36? Break that down for me. Break it down. 6 times 6. 2 times 3, 2 times 3. So I get 2 squared times 3 squared, yes? So how many factors will this have? How do I do it? I always do it the same way, right? So it'll be 2 plus 1 times 2 plus 1. 3 times 3, there will be 9. There's an odd number. Why? Because right in the middle, the number that gets paired with itself is 6. Now, does that make sense? 9 goes with 4. So most numbers, every number goes with a completely different number. But if I have a square number, there's going to be one number right in the middle that goes with itself. Right? So now the square root of 36 is 6, and I'm like, oh, 6 is the dude in the middle. So once I hit him, I know I've hit the turnaround point. So if I go to make this guy's list, it'll be 1, 2, 3, 4, 6. Sweet, right? And then 9, 12, 18, 36. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So when will I get an odd number of factors? If I have a number that is a square, a perfect square. Right? What are the factors of 4? Odd number, yes. So every perfect square will have an odd number of factors. Because there's one number that gets paired with itself. Okay, maybe. Now, let me ask you what you know about this next idea. Does everybody know what this means? Greatest common factor, kick ass. So sometimes people will say it and not even realize what it means. So greatest, that's the biggest, common, everybody's got it, factor. Multiplication piece, right? So it's the biggest thing that all the numbers have as a factor that they have in common. So the most basic way to find a GCF is to make a list. So for example, if I want to find a GCF, and here's how we write this, by the way. I want to find the GCF of 12. No, let's do 24 and 18. So some of you guys should obviously be able to figure that out without doing anything, but the way you would show students is going to highlight the 3 words in GCF. I'm going to make a list of all the factors and see what the biggest ones are they have in common. So if I want to do 18, what are the factors of 18? And then 24? Remember, square root of 24 is 5, so now I've hit the turnaround point, yes? So of course, what's the biggest number they have in common? 6. All right. Notice, now listen, this is a coincidence, but it actually leads to a general approach. What is 24 minus 18? So either they are both multiples of 6, or they're both multiples of 3, or some other factor of 6. If 2 numbers are 6 apart, maybe they're in the multiples of 6 list. You guys with me? So, just to show you a counterexample, are 3 and 9 6 apart? 3 and 9. Are they 6 apart? Yes, but are they in the multiples of 6 list? No. But what goes into 3 and 9? A factor of 6. So if I take the difference of 2 numbers and try to get the greatest common factor for it, the answer has to be that or a factor of that. So if I have 2 numbers that are 15 apart, the GCF is either 15 or 5 or 3 or maybe 1. 2 numbers don't have to have anything in common, correct? Except for 1. I don't know if you guys are with me. Do you actually have to ever do what I just said? No. It's just a neat little thing about our number system. Jeff, do you actually have paper? What the? Did I run out of paper again? Yes. I'll be alright. I can steal some of this. Yep, okay. So what about if I have some bigger numbers? Oh, sorry. I gotta do the other ones for GCF of 18. What did I say, 18 and 24? Yeah. This first way is called, you're not gonna believe it, this is called the set method. Because we made 2 sets of numbers and then we just saw what they had in common. The biggest thing they had in common. So they have 1, 2, 3, and 6 in common. So what's the biggest thing they have in common? 6. So if you make a set of factors for each number, I can then compare and see what do they have biggest thing in common. Because that's literally what GCF means. Now, do we want to do this all the time? No. Screw that. So there's got to be some better ways. So what about if I use prime factors? I know. Beep, beep, beep. So if I take 24 and 18, go ahead and break those down real quick. Take them down to the prime factors. me just ask, is everybody cool with that? You guys got all that same DNA? Yeah. What's the most twos that they both have? 1, right? This poor little dude only has 1. What's the most threes that they both have? 1. So if I take the 1, 2 and the 1, 3 that they both have, I'll get the biggest number they both have. Does that make sense? So it's another example of me building a number up from its pieces. I got the same answer we did before, correct? This is a much better way to do it because I don't have to make all the factors. I actually just make the answer from the pieces. So what's the shortcut? I just take the smallest exponent on every element. Smallest power on 2 is 1, smallest power on 3 is 1. Multiply them, I'm done. I got the GCF. Okay, maybe. Oh, that's right. So let's try a bigger number. Bigger set of numbers here. Let's see. We're not going to do the set method on this, right? Once you get to this size of number, you're not going to do set method. Oh yeah, sure. I'm sorry. Is that right? Sorry. Okay. So go ahead and make prime factor trees for 48 and 92. Oops. $92 doesn't go too far, right? If you're not sure what to do with 92, it's even, so you can divide it by 2. I haven't shown it yet. Here we go. What'd you guys get for 92? What are the factors? The prime factors. Yeah, good. So then you get 2 squared times 23, right? Okay. So that's kind of a bigger number that only has a few pieces to it. That's okay. So if I want to try to piece together the GCF, do you see between the two numbers I have 2s, 3s, and 23s? Yes? What's the lowest power on the 2? 2. So I know I'm going to have 2 squared. What's the lowest power on the 3? How many 3s does this guy have? How many 3s does this guy have? This guy has 2s and a 23, correct? So how many 3s does he have? None. That literally means 3 to the 0. No 3s. And what is 3 to the 0? Is 1, right? So it's got no 3s. So what's the lowest power I see on the 3? 0. Yes? I want you to understand, if the power is 0, that literally means it's got none of those things. Does 92 have any 3s? So it's got 3 to the 0. So when I say, what's the lowest power on the 3? 0. What's the lowest power on the 23? 0, because the first dude ain't got no 23s. Right? So then what's the GCF? Freaking 4, yeah. And real quick, what is 92 minus 48? That's 94 minus 50, right? 44. So either 44 was going to be the answer, or a factor of 44. What was the answer? 4. A factor of 44. Sorry, who's, yeah.
So, sorry, I'm exhausted.
I understand.
So, for the GCF, you, got the lowest power, is it the lowest numbers power, or just the lowest power out of all of them?
So I look, do you see what I mean? I'm looking at everybody's pieces. There's 2s, there's 3s, there's 23s. So what's the lowest power in the 2? 2. What's the lowest power in the 3? 0. What's the lowest power in the 23? 0. So if I put all that together, I get 4. 2 squared times no 3s times no 23s is 4.
Oh, yeah.
So you only include it in the GCF if it's something they both have. So you can even look at it like that. They both have 2 2s. They don't both have 3s. They don't have 23s, both of them. So then I'm not going to include 3 and 23, just the 2 2s. Okay. Dear God, Jeff, is there a better way to do this shit? Yes, there is. But before we do that, we have to do a little proof. Oh boy. Oh geez. Okay. Somebody remind me. Okay. How do you read this in English? Alm and alm. No. What does that say? No, other way. If A divides M, so A goes into, you can think of, right? And A divides N. So if A goes into M and A goes into N, you with me? Okay, so something is going to happen. I'll tell you what the answer is, and then we'll prove it. If A goes into this number and A goes into that number, A goes into the difference of the two numbers. And real quick side note, we're just assuming M is the bigger number. Is that okay? So the difference comes out positive? In general, it doesn't matter, but that's okay. If A goes into a number and A goes into... So, can somebody give me a number that 6 goes into? Second? 36. So 6 goes into 36. So let's do a concrete example of this shit. Yes? Concrete example. Please, Jeff. All right. 6 divides 36. Yes? Somebody give me a number bigger than that. An interesting number that 6 goes into. 48. My claim is 6 should divide 48 minus 36. Well, what is 48 minus 36? 12. Now, is that true? Is that true? Does 6 divide 12? Does 6 go into 12? Yes. Okay. So why does this make sense? Do you all agree with me? All right. If 6 divides into something, if 6 goes into a number, isn't that number in the list of multiples of 6? 6, 12, 18, if I keep going, I'm going to hit every freaking number that 6 goes into, yes? Is that, you guys with me? Okay. So if I start counting by 6s, I'm going to hit 36, I'm going to hit 48. If I have two numbers that are in the list of multiples of 6s, don't they have to be a multiple of 6 apart? How do I make the multiples of 6? How do I chant it? I just keep adding 6. 0, 6, 12, 18. If I pick any two of the numbers that are in there, they have to be a multiple of 6 apart because I make them by going by 6s. Yes? So if 6 goes into one number and 6 goes into another number, 6 has to go into their difference. That is related to the little thing I told you about earlier. If you take the difference, you can see what the GCF might be. What does that have to do with anything, Jeff? Okay, here we go. Can you imagine doing this problem the way that we've been doing the problems? Well, this is not too bad yet. Nah. Let me get a good one. Here we go. You can do it, buddy. Write something. There it is. Look at that go. Okay. That's a little big, Jeff. All right, let's make this a target. We'll do this next. Let me make it a little bit smaller of a problem. You could do it, buddy. There we go. That's perfect. Okay, that's perfect. Okay, we'll do this one second because I have an even better shortcut. Whatever the GCF is for 42 and 128. Yes, once the numbers start getting bigger, you definitely don't want to make a list of all the factors. You definitely don't want to freaking do a prime factor tree. Holy shit. There's got to be a shortcut. I want the number that goes into both of those numbers, the biggest number. Yes, that's what GCF means. We just figured out that if there is a number that goes into those numbers, it goes into their difference. Isn't that what we just said? So I'm going to take the freaking difference and make 128 become smaller. Whatever the answer is, whatever the number is that is the answer, it does what? It goes into 42 and 128. You with me? You say this again. Isn't GCF the biggest number that goes into both numbers? Okay. So whatever the answer is, it goes into both numbers. If I take the difference, the thing we just talked about, that number has to still go into those two numbers. So I can knock down, when I get these big ass numbers, I can start to subtract and make them smaller and make the thing easier to look at. So what is 128 minus 42? 86. So then we go, this equals the GCF of 42 and 86. What do you think I'm going to do now? Do it again. So now if I take 42 away again, what do I get? 44, yes? Are you guys with me? And if you want to do it again, you could do it again. And you got 42 and 2. But what obviously is the answer? What's the biggest number that goes into 42 and 2? Freaking 2. Isn't that nice? Because the only thing that could really make these problems difficult is if I make the numbers big. Well, now I've given you a way to knock the numbers down. Now, real quick, what did I actually just do? What did I do 3 times? I did this 3 times. What did I do 3 times? I did something 3 times, yes? What did I do? Subtracting? 42. What's repeated subtraction? Okay, so then there's an ultimate shortcut. If I just divided, what's 128? Help me out, anybody. What's 128 divided by 42? Do that in your calculator. Has everybody got this written down? Go ahead, Nick.
Oh, no, I'm just.
Sorry, do it again. 3 remainder. Remember? Yes, it is, because 3 times I was 126. I like. So do you see how that relates to this? What's the 3? How does that relate to the concrete thing I did? I did 42 subtracted 3 times, yes? And what's the 2? It's a freaking remainder. That's the thing that was in the end, right? So you could skip all this shit. If you divide and get the remainder, that you could replace the big ass number with that remainder number. Go see it. Go see it. So if you understand that if you subtract 2 numbers, that new number you get still has the biggest factor with that first number. They still have the same answer for the GCF. That's the whole thing we did above this. Then that only naturally leads to division, because you're going to want to subtract until you get a nice number. Well, then you can divide instead of doing a billion freaking. Look at the first number, 54 and 9,072. Can you imagine subtracting 54 so many times? Yes? I don't want to do that shit. So, what can I do instead? So if I want, what was it? 54 and 9,072. So somebody help me out. What am I going to do? Yeah, what's 9,072 divided by 54? Do it again, sorry. 168 point stuff? Or is that exactly 168? Damn it. Well, I'm sorry, so that's easy. I just made that up out of nowhere. So of course I made up something that actually works. When I don't want it to work, it works. Do you guys understand what just happened? What's the answer then? Now you gotta be careful. 54 goes into this evenly, yes? Because what was the remainder? Nothing. So that means 54 goes into this. So what number goes into both of these? 54. Yeah. So if it goes in evenly, you've got the answer. Yes? What's the GCF of 8 and 16? Freaking 8, because 8 goes into both, right? That's what we just figured out since it went in evenly. Darn it. All right, let me see. I gotta make one that doesn't work that nice. Well, I should. What if I do this? Yeah. What if I make this 9,000? You could do it, Jeff. What are you going to make it, buddy? Yeah, 9,099. There we go. So what's 9099 divided by 54? 9099. What do you get when you divide those? How'd you know it was remainder 5? Oh, no. Gotta be careful. So you got 168.5. You guys, if anybody else is trying it, is that what you guys got? Is that what you guys got? Anybody? Yes. Okay. Let me show you 2 ways to figure out the remainder. The remainder is not 5. Right? The 0.5 is 5 out of 10, which is something out of 54. Right? Okay. What's 168 times 54? And this is really the stuff we've done before.
9,072.
Good. And then what's the difference? So if I do 54 times 168, I get 9072. And what's 9099 minus that? 27. So that's the remainder. Or, what's 0.5 times what I divided by? What's half of 54? 27. Either way tells you what the remainder is.
So if there is no remainder,
Then the small number is the answer,
okay.
because that's the number that goes into both. If there is a remainder, I can rewrite this now. I can replace the big ass number with 27. How many times could I subtract 54 from this? You could do it. We did the work already. How many times could I subtract 54 from this? 168. What would be left at the end of that? 27. So I just did, where'd it go? I just did this without having to write it 168 times. I know I would have written it 168 times, and I would have gone insane around the 50th time. In the corner here, babbling to myself. And what would be left over is 27. What's the GCF of 54 and 27? Well, it's 27 because 27 goes into 54. Okay. All right, guys. I'm sorry. Today was a very math heavy in a math class, though. So I mean, you have to expect that. So you're not going to be surprised about the next topic, which is going to be LCM, least common multiple. Which, when it's in fractions denominators, we call it LCM. It's the same idea. 5.2. Still 5.2 again. Oh, cool. All right. All right, guys. I'll see y'all next week. Have a good weekend. Bye-bye.